Here we go with Unit 4. We're looking at Topic 8, the Intro to Acid-Base Reactions. So we've had a little snippet of acid-base reactions so far, and now we're going to go a little deeper with them and get to know them better. So we're going to determine strong acids and bases, be able to recognize them, to help in writing Netionic equations for acid-base reactions, and to determine what are called conjugate acids and bases from our chemical reactions. So we're going to start with conjugate acid-base pairs, or conjugate acids and bases. So it says an acid like HNO3, so that's one of our acids because it's got that hydrogen out front. That's how we can recognize it. When it reacts, it'll give away that hydrogen ion and it forms NO3-. So when we remove that hydrogen ion, remember hydrogen ions are going to be H and they're going to be positive, H+. So when we remove that, we get nitrate left over and it has a negative charge. This ion, the nitrate ion, is called the conjugate base of the acid. So we can look at our chemical reaction here. So this is just a reaction to show how the acid breaks apart. So we've got our acid. It gives away that hydrogen, so it splits off that hydrogen. If we had a base mixed with it, that base would take the hydrogen. And then it forms what's called the conjugate base. Now, where does that term conjugate base come from? Well, if we were to analyze the reaction going the other direction, okay, so say we were to reverse this reaction, the nitrate would be gaining a hydrogen to form our acid. So the nitrate in that case, since it's gaining the hydrogen, would be acting like a base. Bases are things that gain hydrogen ions. So our chemical, our nitric acid acts like an acid going to the left, going from left to right, and our nitrate ion acts like a base going from right to left. So that's where that term comes from. It's basically the conjugate base is what is formed when an acid reacts, when it gives up that hydrogen. Okay, so we could look at any acid. If we remove a hydrogen ion from it, what's formed is the conjugate base. Now we can do the same type of thing with our base. So a base like sodium hydroxide, when it reacts, gains a hydrogen ion and forms water. This is the conjugate acid of the base. Okay, so the OH from our base reacts with, and what I'm missing here is our hydrogen, right? So our base has to gain a hydrogen ion. Sorry, I was missing that part. And our hydroxide and our hydrogen make water, and that is our conjugate acid. So the hydroxide is the part that's gaining the hydrogen, so that forms our conjugate acid. Okay, so when we're dealing with a base, whatever gains the hydrogen when it gains that hydrogen, what it forms is called our conjugate acid. So we're going to take a look at some more examples of this and try some. Now, something to keep in mind is since a hydrogen ion is positively charged, when it is exchanged between substances, their charge will change as well. We don't just look at the elements, we look at the charge. And that's going to be important not only in acid-base, but in our next section in redox reactions. So when an acid loses hydrogen ion, its charge goes down by 1. Okay, so because we're getting rid of something positive, our chemical that's left over loses charge or goes down by 1. It becomes more negative. So if it was at 0, it becomes -1. If it was a -1, it becomes a -2. If it was a +1, it would go down to 0. Okay, so it just depends on where you're starting. We're going to drop it by 1. When a base gains hydrogen ion, the charge increases by 1 because we're adding that positive ion, that hydrogen ion. So we're going to increase the charge. So if we're 0, we're going to go to +1. If I was at -2, I'm at -1 now. If I'm at -1, I'm going to go to 0, right? So this gives you some ideas on what's going on there. Let's practice writing some conjugate bases and conjugate acids of our chemicals. So we're going to start with the conjugate base. So all of the things listed here are going to be acids. So that means they're going to give away hydrogen ion to make the conjugate base. Okay, So if I want to make the conjugate base of this first acid, I'm going to take away one hydrogen, so I'm going to be left with one H in the front. I'm going to leave the rest of the chemical, and then if I give away something positive, I'm going to make it one more charge negative, okay? So this would be HSO4 minus. That is the conjugate base of sulfuric acid, H2SO4. So we're going to keep going with that same pattern. We're going to remove a hydrogen always off the front if it's listed there. And we get C2H3O2. And then we lost one hydrogen, so we're going to make it more negative. Okay, it started neutral, so it's going to be a negative charge now. Okay, now this is our acetate ion. This is called acetic acid. This is vinegar. This is what we used. We've used in multiple areas. You guys made solutions with acetic acid. We could not with this one because the H3, that's part of that polyatomic ion, we could not take off more hydrogens. Those are trapped in that ion, right? So that's something to be aware of. Now this one already has a charge, H2PO4. So if we remove another hydrogen, or we remove a hydrogen from it, we're going to be left with one. We've still got the PO4 ion for the rest of the chemical, and then we're going to make it one more negative. So now it's going to be a 2 minus charge. So that's how we're going to form conjugate bases. On the other side, it says what is the conjugate acid of the following. So that means these are bases, and if we want to make an acid, we're going to gain a hydrogen ion. So that means that if we're gaining a hydrogen, instead of becoming more negative, we're going to become one more positive. Okay, so we're going to stick the hydrogen in the front, put the rest of the chemical, and then we want to drop that charge, or excuse me, increase that charge. If we think number line, right? We got 0, -1, -2, 1, 2. We want to increase that charge by 1. All right, so we'll be a negative ion at that point. All right, here we've got NH3, so we're going to gain a hydrogen. This might be familiar. We would typically put it in front, but these already have these hydrogens. We're going to write it as NH4, and again, it's already a 0 charge, so we're going to increase it and go to +1. So now you can see we've got ammonia, NH3. If it gains a hydrogen, then it becomes NH4 plus, ammonium ion, and that's a common one that we'll see there too. All right, and this last one, if we have PO4 3 minus, we gain that hydrogen, so we have HPO4. If we are at a 3 minus charge, -3, we gain, we're going to be at a 2 minus charge. Okay, so that's how we go between conjugate acid-base pairs, how we form these. So these are known as conjugate acid-base pairs. So looking at like number 1, you've got your acid and its conjugate base. So that would be called a conjugate acid-base pair. Okay, similar, say we looked on number 6, we've got a base and its conjugate acid. So that's a conjugate acid-base pair, right? So let's take a look at another conjugate acid-base pair. So like we were looking at on the last one. So I defined conjugate acid-base pair. It's an acid and a base that differ only by the presence or absence of a proton or hydrogen ion. Every acid has a conjugate base and every base has a conjugate acid. Okay, so let's label them just like we did in the last on the last slide. If you want to pause and try this one on your own, it'd be a good idea, and then you can play and check them. So our chemicals here, I always find my acid first, personally. So my acid is my chemical that gives up hydrogen. Well, on my reactant side on the left, the only thing with hydrogen is HNO3, or excuse me, HNO2. So that has to be my acid. And then I'm going to go ahead and find my conjugate base because I like to kind of pair those up. So when it gets rid of the hydrogen, it becomes NO2 minus, so that's my conjugate base. And those two are a pair. Now my chlorine has to be my base because it's my only other reactant. We can see that it gains the hydrogen, becomes HCl, and that is the conjugate acid. And you can see that H in front, so it's acting like an acid there. So here we have our conjugate acid-base pair. So we can always pair those up and see how they relate to each other of a hydrogen ion. Changed my slide a little early. All right, we are going to take a look at this question. We've got some different parts to it. So we're going to find, first, I want you to write down which substance is the acid in the reaction. So choose A, B, C, or D as your choice there. And then you're going to choose which substance is the conjugate base of the acid, A, B, C, or D. And then which is the base and which is the conjugate acid. So take a minute and try that out, and then we'll check it. Okay, so hopefully we've worked this out. So looking at our chemicals, our acid is going to be our chemical that loses its hydrogen. So we've got lots of hydrogens happening here. So NH3, if we look at the products, it gains a hydrogen, so that's not our acid. Our water, though, goes from H2O to just OH. So this is our acid. Letter B is our acid. I'll put A for acid, or I'll label it. All right, which means our other reactant has to be our base. So letter A is our base. All right. And then number 2 says what substance is the conjugate base of the acid. So what our acid becomes when it gives away its hydrogen is OH. This is our conjugate base. So that would be letter D. And what our base becomes when it gains a hydrogen is our conjugate acid. So that would be letter C. All right. So on the left side, we'll always have our acid and base. On the right will always be their conjugates, okay? So now we're going to look at our strong acids. So these acids, when in aqueous solution, will dissociate or dissolve completely. So these are covalent compounds. If we look at this list down here, we've got hydrogen and chlorine. Those are nonmetals, hydrogen bromine, hydrogen iodine. So all of these listed down here are nonmetals. That would make them covalent compounds. But what makes acids different than a regular covalent compound is that they are allowed to break off that hydrogen from it, the chemical. So when they ionize or they break into ions, we get hydrogen, a hydrogen ion, and then whatever's left over is our negative ion with a charge that balances our number of hydrogens. So for instance, HCl, when it's aqueous, it's not HCl, it's H plus and Cl minus, okay? We can separate those out. So all of these acids that are listed here are strong acids, which means those ions, if I put HCl into water, they're not going to stay together. It's not going to stay as the covalent HCl compound. It's going to break into hydrogen and chlorine ions. Same with hydrobromic acid. So it's going to break into hydrogen and bromine ions. So all of these acids will do that. So when we are writing net ionic equations, anything that's a strong acid is going to separate into its ions, okay, when they're aqueous. So we've got hydrochloric, hydrobromic, hydroiodic. Those are chlorine, bromine, and iodine. They're all those halogens, in group 7 on our periodic table. This does not include fluorine, okay? Fluorine's too electronegative for it to ionize like this, okay? It doesn't work that way, but the others do. Our other 3 acids involve polyatomic ions. So we've got nitric acid. We've dealt with our nitrate ion. We should be pretty familiar with that. That's one that always dissolves anyway. So keep that in mind. We have perchloric acid. So it's that perchlorate ion. And then we've got sulfuric acid, so our sulfate ion. That's the only one with more than one hydrogen. We call it a diprotic acid, so 2 hydrogens or 2 protons, because a hydrogen ion is just a proton. So those are our 6 strong acids. It sounds down at the bottom. These need to be committed to memory. Okay, you need to make some flashcards. You need to know your 6 strong acids. All right. 3 of them are pretty straightforward. Our 3 halogens, chlorine, bromine, iodine. Throw a hydrogen on them. We got nitric acid, perchloric, sulfuric acid. So we got to know these. Okay. Similarly, we also have strong bases. So our strong bases are the bases that, when in aqueous solution, will dissociate completely. Now, our bases are already ionic compounds. So they dissociate into the regular ions. Notice that they all are a metal hydroxide. So you've got a group 1 metal hydroxide or a group 2 metal hydroxide. Well, what does that mean? It means all the metals listed here are in group 1 of the periodic table. So memorizing your strong bases is way easier than your strong acids. Any metal in group 1 or any metal in group 2, when you pair it with hydroxide, you have a strong base. And these ones will separate completely. So when we write like sodium hydroxide and it's labeled as aqueous, we can separate it into sodium and hydroxide ions. Okay, so these all dissociate, they dissolve, they're going to break apart in solution. Okay, so our strong acids and bases, we want to know those, we want to commit them to memory, and that's going to help us in writing their net ionic equations. So now we're going to look at net ionic equations. This is our last part of this section, of our acid-base section. So we've written net ionic equations, so this is going to give you a little more practice with that. But for acid-base reactions, there's one little thing we have to take into consideration. So the same process applies. We still want to split up some of our chemicals into ions. We're going to keep anything that is a solid, liquid, or gas exactly as it's written. We're not going to change those. Now, the difference here, what makes acid-base reactions different? Our strong acids and bases will separate into their ions, while all other acids and bases, which we call weak acids and bases, will stay together, even when labeled aqueous. That is huge. Okay, so if we look at a reaction and we recognize that it is an acid-base reaction, before we start breaking everything down, we are going to ask ourselves, is it strong or weak? Okay, how do we know if it's strong or weak? Well, that's why we had the list on the last couple slides. So if it's a strong acid, if it's on the list, it's going to separate into its ions. If it is not on the list, if it is weak, it's going to stay together. So I always think it's strong and independent, meaning they separate, or they're weak and need a buddy. They have to stay together. Okay, so we've got a reaction here. We've got HBr, hydrobromic acid, plus AlOH3, aluminum hydroxide. So we've got an acid plus a base. We're making water and aluminum bromide, water and salt. Okay, so like I said, first question, strong or weak? So our first chemical here, hydrobromic acid. You want to look at your list and determine, is it strong or weak? Well, it is on our list, so it is a strong acid. Aluminum hydroxide is not on our list, so it is a weak base. It's not in group 1 or 2. Aluminum isn't, so it's weak. So The strong acid is going to separate into its ions. The weak acid, we're going to copy exactly as is. And I'm going to wait to do that, so I have space. We're going to copy it down. We're going to keep it together. I'm going to put it like that so I keep it together. Our liquid water, we're going to keep together. We're going to just copy it down. And then on the right side, our salt, we're going to determine if it separates or not based on its state of matter. Okay, so this one's aqueous, we'll separate it. All right, so let's try creating our complete ionic equation. All right, so we're going to make the complete ionic equation. So we'll start with our strong acid and separate it into its ions. So we have hydrogen, H+, which is aqueous, and bromine, Br-, which is aqueous. All right, we have a 3 in front of the whole chemical, so that's going to apply to both ions. 3 hydrogen, 3 bromine. They both stay aqueous because the state of matter won't change just because we separate them. All right, our weak base, we're going to leave together, so we just copy it down. Don't change anything, don't add any charges, nothing changes. Our water, again, we're going to copy down. It's a liquid, so nothing changes. And then our aluminum bromide is our aqueous solution, so we do want to separate that. That's our salt. So we're going to separate it into aluminum and bromine. We have 3 bromine that are negative. Aluminum has a 3+ charge, and I didn't leave a space, so that is aqueous, and this one is aqueous. So that is our complete ionic equation. We didn't separate as many things as we do in a lot of them. Now we want to look for our spectator ions, so things that do not change from one side to the other. Hydrogen is H+ on this side, and it's in the water on the right side, so it changes. Bromine is Br- on the left, aqueous, and it's 3 Br- on the right, aqueous. It does not change, so that's a spectator. The aluminum hydroxide changes because our aluminum becomes an ion, so we got to keep that, and our water we got to keep. So we can only remove our bromine, so we get 3H+ aqueous plus aluminum hydroxide. And again, we're keeping that one together because it's a weak base. It doesn't actually ionize in water very much. Only a tiny, tiny fraction of it will break apart. So we leave it together to show what most of the chemical looks like. Yeah, aqueous. So I'm just copying everything down that I didn't underline there. And that's our net ionic equation. So we'll try one more on the next slide. So let's take a look at this one. We've got 2 HCl, so we've got hydrochloric acid plus calcium hydroxide, making 2 water molecules and calcium chloride. So again, your number one question when you recognize it's an acid and a base is we want to ask, is it strong or weak? So HCl, think about it. Is it on your list? Yes, it is. So that is a strong acid. Calcium hydroxide, is the calcium in group 1 or 2? Yes, it is. So that is a strong base. So what does that mean? It means both of these are going to separate into their ions. We're going to keep the water all together because it's a liquid, and our calcium chlorides is aqueous salt, so we'll separate it. So we get 2 hydrogens ions, aqueous, and 2 chlorine ions that are aqueous. Plus, we have our calcium ion. That's a 2+ charge, it's aqueous. And we have 2 hydroxide ions that are aqueous. So then we bring that 2 to the front, just like when we separated ions. Our water, oops, that's an arrow. Our water stays together, 2 water molecules because they're liquid. And then we separate our calcium chloride. So we have calcium 2+, aqueous. And I see a lot of students still messing this part up. And we have 2 chloride ions that are aqueous, okay? We do not write Cl2-. That does not exist. That is not a real thing, okay? You got to bring that 2 to the front. All right, let's look for our spectator ions. So we've got hydrogen on the left as an ion, no hydrogen ion on the right. I got chlorine as an ion on the left, and I got it on the right. So this one is a spectator. I got calcium ion on the left, I got calcium ion on the right. I got hydroxide on the left, no hydroxide on the right. So we are down to 2 hydrogen ions and 2 hydroxide ions. And that will make 2 water molecules. And that is our net ionic equation. So when we have a strong acid and a strong base, because they separate, this is always going to be our net ionic equation for a strong acid and a strong base. Okay, always. So that's something to keep in mind. We can simplify things. So that's our acid-base stuff. So we can recognize and find conjugate acid-base pairs. They're only different by 1 hydrogen. We can recognize our strong acids and bases. So we got to make sure we know those. Definitely make some flashcards if you need to. We can write our net ionic equations from our reactions and separate our strong acids and strong bases when we do that. So those are the main things for acid-base reactions. Let me know what questions you have. Thanks, guys.